All right, here we are for conceptual momentum problems. There's 12 of them. We're going to take a look at the second 6 here. Starting with problem 7, the center of mass of a rigid object of arbitrary shape. Where is that center of mass for just objects in general? Shape doesn't matter. Where would the center of mass be? Will it always be inside the object? Can it be outside the object? Does it depend on how the object's moving or on your frame of reference? And you say, well, that center of mass, right? You say, well, point is, what I'm going to say is, it really, I mean, if you think about it, isn't it true that the answer has to be either A or B? It can only be in, or sometimes it can be out. You know what I mean? It's kind of got to be one or the other. You know what I mean? How the thing's moving doesn't affect where its center of mass is, right? Unless it's changing shape or something. And depending on the frame of reference, no matter where you call x equals 0, I mean, you'll have a different position value if you call it for the center of mass, but it's still the same location on the object. You know what I mean? Or compared to the object. So actually, the correct answer here is going to be B. Can you think of an object where the center of mass is outside? And you might think, for example, of a donut, right? And you say, hey, in a donut, the center of mass is in the hole, right? Okay, it's not on the donut itself. Or a horseshoe was something someone said in class the other day. They said, yeah, if you have a horseshoe, the center of mass of that horseshoe is not going to be on the shoe itself. It's going to be kind of in the middle there, right? The really important example, or example I'd like to point out to you, is the Fosbury flop. All right. I'm going to provide a link to a little video on it. It's a really interesting story and interesting to see. So Fosbury flop, another great example. So that's it. Okay, problem 8. All right. It says, compared with the kinetic energy of its center of mass, the total kinetic energy of a system is... so let's talk about what we mean by this: kinetic energy, the center of mass, and total kinetic energy. You'll recall that I hope that we derived a formula for the velocity of the center of mass of an object. We had position of center of mass, and then we went ahead and we took the derivative with respect to time and got velocity of the center of mass. We took the derivative with respect to time and got acceleration of the center of mass. Velocity of the center of mass just comes out to be add up all the individual particles' masses times their individual velocities, and then just divide by the total mass. All right, the sum of all the mi's. Let's just say m total. All right, and that'd be the velocity of the center of mass. So you're asking here is about kinetic energy. It's kind of weird. I don't know if this question really belongs in this unit. Well, it kind of does. Kinetic energy of the center of mass. You say, well, kinetic energy of the center of mass, then that would just be 1/2 the total mass times the velocity of the center of mass squared. Okay, that's what we're talking about. Kinetic energy of the center of mass. All right. So in other words, I'm treating all the mass, right, like it's moving like the center of mass is moving. That it has the same velocity as that center of mass, and all the mass is focused there. What would that kinetic energy be for that? If I took all the mass and focused it on a particle and looked at how fast that center mass is going. All right. I'm comparing that to just adding up the total kinetic energy of the system. So adding up all of the 1/2 mi vi squareds. Make sense? So that would be my total kinetic energy of all the particles moving around in the system. So the question is, the total kinetic energy, will it always be less than the kinetic energy of the center of mass, equal to the kinetic energy of the center of mass, or greater than or equal to the kinetic energy of the center of mass, or will it depend on what system you're talking about? And so basically what I'm going to say is, can you imagine having a person who is like, maybe it's a diver diving off a diving board, right? And you say, hey, when that person jumps off, they could just kind of stand there and just kind of go hop, right? And fall like this, right? And just fall very rigidly. Or they could hop off that diving board, right? And when they hop off, they go and they do all kinds of weird tricks and spins, and they go into a tuck, right? Okay, right? Or they wave and they flail their arms around and stuff. right? And they're whipping those arms back and forth, right? And the legs back and forth, thrashing around as they fall. You say, now look, both of these cases, the center of mass is going to be just moving along, right? All right, with a certain velocity. If I take the total mass of the diver times center mass squared, it's going to be the same for both. But if I add up, doing this with my arms and legs rigid versus them all flapping around, there's going to be more kinetic energy. All the parts adding up will be added to more kinetic energy than if we just go rigidly. So you say, so yeah, my total kinetic energy is going to vary, and it can be greater than the kinetic energy of just the center of mass moving, right? If I have all this other thrashing and wiggling around going. So I can have a bunch of parts of the system moving all kinds of crazy ways, but the center of mass just moving smoothly. This is going to be more kinetic energy than that. So, okay, so greater than or equal to, all right, is going to be the best answer for that one. All right, number 9. Number 9 asks, yes, suppose a ping pong ball and a bowling ball are rolling towards you. Both have the same momentum, and you exert the same force to stop each of them. How does the time intervals to stop them compare? So say I have rolling towards me here, say it's a top-down view. I've got a ping pong ball. Now, a ping pong ball has a teeny tiny little mass, right? And I've got a great big bowling ball, right? Which has a great big mass. Now, we're told that they both have the same momentum, which means that m times v for this equals to m times v for this. So the bowling ball with a huge mass might have a small velocity. The ping pong ball must have a way bigger velocity. So that this mv is going to be the same as this mv, right? Same momentum. So the question now is if I want to stop them, and I push on both with the same force, all right, to try to stop it. Okay, and I push against them with the same amount of force, all right, wonk, 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 wonk. The question is, what's going to how the time intervals that I'm pushing compare? So you say, well, if I think about stopping them, I'm changing their momenta, aren't I? I'm applying a force and changing momenta. You say, this should call to mind the most important formula in this unit, which is the impulse is the change in momentum, right? Both these guys have the same starting momentum, and they both are going to end with a momentum of 0, so they have the same change. And if I push with the same force, that's going to be the same duration, isn't it? I'm going to have to integrate that for the same amount of time to get the same answer out. So basically, the times are going to be the same. The times are the same, all right? And that would be choice B. Both take the same time. Okay, question 10. All right, we're going to do 9 and 10. I'll use the same sketch for both. Same setup. Ping pong ball, bowling ball going towards you, identical speeds, right? I'm sorry, identical momenta, very different speeds. Identical momenta. You're going to apply the same force to both to stop them. What about the distances that you push through to stop them? Okay, now if I just hold my hand rigid, right? What we're doing is we're trying not to just hold still and stop it. We're like pushing with it, making sure that force stays the same the whole time that we're stopping it, right? The question is, what are the distances it takes to stop them in? And you say, well, interestingly, if I'm going to analyze this, now I'm thinking about applying a force through a distance. So if I'm talking about applying a force through a distance, now I'm not thinking about integral f dt. I'm thinking about integral f dx. I'm thinking about work, not impulse. And work changes the kinetic energy of the system. So I'm thinking about the fact that they have these starting kinetic energies, and I want to take that kinetic energy away. How much work do I have to do? Well, whereas before, mv equals mv equal momenta, will they have equal kinetic energies? And the answer is no. If they have equal momenta, momentum is mass times velocity, right? Maybe one of them has, I don't know, what do you think? How does the mass of a bowling ball compare to the mass of a ping pong ball? I don't know, it would be 1,000 times more? 2,000? I don't have a good mental image of that. They're so different. Let's just say that this mass of the bowling ball is 1,000 times the mass of the ping pong ball. Then its velocity to make this be the same momentum would be 1/1000th, wouldn't it? Do you see what I'm saying? So the bowling ball has 1,000 times the mass of the ping pong ball. It would have to have 1/1000th the velocity to get the same P. Well, when I go to consider kinetic energy now, so say this is the kinetic energy in blue, that's the kinetic energy of the ping pong ball. If I'm going to go ahead and compare it to the bowling ball has 1,000 times the mass, so I'd multiply by 1,000. But the velocity is 1/1000th as big. And I'm going to square velocity. So my kinetic energy will be 1/1000th as much. Do you see that? So with equal momenta, bizarrely, the smaller object, smaller mass, right? Equal momenta, smaller mass has bigger velocity. And since velocity is more important in energy calculations, it's squared. It will the ping pong ball will have more kinetic energy than the bowling ball would. If it has more kinetic energy, I'm going to have to do more work to take that energy away, right? I have to remove more energy. And so I would have to push, in this case, through 1,000 times the distance to stop the ping pong ball than the bowling ball. All right? So the ping pong ball will take longer distance to stop. And if you think about it, well, basically that's it. The deal is, yep. It's got more kinetic energy. Okay, I'm just gonna leave it at that. Okay, let's go to problem 11. All right, problem 11. A golf ball is fired at a bowling ball that's initially at rest, and it sticks to it. I don't know why a golf ball would stick to a bowling ball, but anyway, so this is going to be one of those perfectly inelastic collisions. They hit and stick. Afterwards, they will be moving together, right? Compared to the bowling ball, the golf ball after the collision would have, let's compare momenta and energies. Well, if the golf ball is stuck to the bowling ball, isn't it true that afterwards then they'll be moving with the same speed, the same V final? So if I want to compare momenta, momentum is mass times velocity. They have the same velocities, but they've got radically different masses. The bowling ball has more mass. The bowling ball would have more momentum. So the golf ball has less momentum than the bowling ball. So you're like, okay, well, then it's got to be either C or D. What about kinetic energy? Well, kinetic energy depends on mass also. Their final velocities are the same because they're moving together, bowling ball and golf ball, but the masses are different. So golf ball has smaller mass, it'll have smaller kinetic energy too. So there you go. It's got less momentum and less kinetic energy. Choice C is the best answer for problem 11. Which takes us to problem 12, the last one for the set. I've got two carts that are put back to back on a track. And A has this spring-loaded piston, and cart B has got twice the mass of cart A. And so I've got those two set up there back to back, right, with the spring compressed between them. Cart B's got twice the mass. When I let go of that piston, right, the spring's going to go unsprung. It's going to go sprung, and it's going to push them apart. How does the magnitudes of the final momentum and kinetic energies of the two things compare? Okay, here is actually what that looks like. Here's my two carts. okay? And they have the same mass. These are made to be weighted to have the same mass, okay? But this one has a spring built into it, okay? So there's a little plunger or piston that compresses the spring, and then the spring would push back. And I can actually kind of latch that into position by pressing this little button, click. And if I push on this pin, it will pop it back out. So I can put these kind of up against each other like so. And if I were to press the plunger, press the pin, it will push them apart. And I'm going to make this one be twice as massive. Okay, this black block of iron doubles the mass of the card. So we could test this if we wished. But let's do the calculation when they push apart. Okay, what's going to happen? So taking a look at it, they want us to compare the momenta, and they want us to compare the kinetic energies of the carts. And you say, well, if I consider these to be one system, I'm thinking about when they push, they're going to push apart, they're going to move horizontally. Taking these as one system, are there any horizontal forces that are going to act on them? Well, ignoring friction and stuff, you say no. There's no outside horizontal force, which means the horizontal momentum before equals the horizontal momentum after for the system. The total momentum before is 0. It's at rest. So the momentum after has to be 0. So however much momentum one of them gains in one direction, the other has to gain an equal amount in the other direction. So those momenta will be equal. So the mass of A times the velocity of A will equal the mass of B times the velocity of the B, right? Just they're in opposite. The velocities are opposite signs. So if I move, they'll add up to 0 if I move to their side. Okay, they're going to be equal but opposite. Okay, so good enough. So now momenta are the same. So on the multiple choice, that gets us to either D or E. Now we just have to talk about what's the kinetic energy is going to be like, right? And so this is the tricky part. A lot of people, their first gut instinct is, well, that spring is going to push on them both. Isn't that force going to be equal and opposite on both carts, right? And so you would assume, a lot of people would assume that energy that was stored up in the spring will then get distributed evenly to both carts, right? That spring between them pushes equal and opposite forces. But that's not going to be the case, all right? And I will show you mathematically first, and then we'll talk logically about why it will be that way, all right? So first, mathematically. Since I know mv and mv are equal to each other afterwards, right, from the conservation of momentum, we got that? Now you say, I know that the mass of B is double the mass of A. So if this is B's side of the equation, this is A's side of the equation. The mass of B, that's 2 times the mass of A, isn't it? Well, for this side to equal that side, the velocity of B must be half the velocity of A then. Is that true? So, I've got my left-right flip-flopped here. I'm going to turn this around. Cart A is the one with this cart with the spring, and cart B here is the one that's twice the mass. So the point is, from this, we know that the guy who's twice the mass will move with half the velocity, right? Okay, and this guy will go twice the velocity, right? Here, can I, ready? Not that you can tell in this short space, all right, in my frame of view here, but 3, 2, 1. Okay, could you tell? All right, the lightweight guy zipped off faster than the big massive guy. 3, 2, 1. Okay. Anyway, which is what we would expect. Okay. All right. But let's go to if I go ahead and I say, now knowing this relationship here, let's talk kinetic energies. The kinetic energy of cart A is going to be 1/2 the mass of A, the velocity of A, the speed of A squared. But what's this going to be? It'll be 1/2 mass of B, velocity of B squared. But the mass of B is double the mass of A. I'm sorry, this is are they equal, is what we're asking here. This is double the mass of A, and the speed is half the speed of A. We just figured out, right? But this is going to be squared, right? See what I'm saying? So the point is, this side of the equation, here, I'll put in blue all of the A stuff. Do you see what I'm saying? I'm going to have 2, but times a half squared. This side is going to be half the size of this side. So the guy that's twice the mass will actually have half the kinetic energy because of the way V is. I'm going to square that velocity, half the velocity, but then square, so I get an extra half term there. Does that kind of make sense? So yeah. So the strange as it sounds, when I do this trick, right, and I have equal and opposite momenta, the one that has less mass has more energy. Okay, so I can see mathematically how that would be that ratio, that 2-to-1 ratio. You say, what about in here? Can you logic through why that happens or how that happens? We said when I release the spring, all right, that spring is going to push these guys apart. And the force on A by B, force back on B by A, you say that force between them is equal and opposite. But this guy has less mass. So equal forces, smaller mass, won't he have a bigger acceleration? And if he has a bigger acceleration, that means he'll move through more distance while that force is applied. And work is force through distance, right? And so if I'm applying that same force through a bigger distance, I'm going to give this guy more kinetic energy than the massive guy gets. In this case, twice as much, right? So the energy is in a 2-to-1 ratio. So 2/3 of the energy goes in the light guy, 1/3 into the heavy guy. Interesting. Okay, so that's it. Okay, because the way that velocity is squared in the kinetic energy term, but not squared in the momentum term. All right, that's good stuff. Okay, that's the things to know and be aware of. That's the conceptual questions for momentum. Don't forget to watch that video on the Fosbury flop. Okay, for problem 7. It's cool. I think you'll enjoy it.